Yeah, thank you, Marcella. Good morning, good afternoon, everybody. Buenos dias todos. So my name is Rainer Schmidt. I'm located here in Karlsruhe in Germany in the headquarters of Bruker AXS. I'm responsible for the automation team here in Karlsruhe, which is also covering the application support of some of our industrial key markets like cement. So we have a whole group here in Karlsruhe supporting the cement community, which is of course also locally supported by our colleagues in the regions, like for example, Renato in Sao Paulo. Today I would like to talk about early or pre-hydration in cement. I would like to share my screen. Okay.
I cannot see your screen.
Can you see my screen?
No.
Oh, not yet. Okay.
Yes, now it is okay.
Okay, perfect. Okay, so there are a couple of areas in the whole cement production process where the properties of the materials are governed by the phase composition. So typically we think about clinker, the cement itself, or what's happening in the preheater. Today I would like to focus on early hydration. The mineral phases of early hydration, they can be easily detected by X-ray diffraction. In fact, that's one of the only methods which is able to catch all this. We can distinguish the different forms of prehydration, so the different phases. Quantification of these phases is meanwhile, since more than 2 years, a routine task. And I will show you that these applications can be easily integrated in the existing methods of an XRD unit. So as already said, when we look at the cement production process, there are a couple of areas where the phase composition is important. And today we would like to focus on this area. So what happens in the cement mill, and also in the silo. And we want to follow what can happen here regarding hydration processes, unwanted hydration processes. So when we think about early hydration, we can find this in the cement mill. This also is pretty related to the type of mill you're using. There's a difference between a ball mill and a vertical roller mill. We need to consider early hydration in the silo, which may lead to lump formation. And in general, early hydration can result in falls or flash setting, because the reactions which occur, which take place, might remove some SO3, some reactive SO3, and this has an important impact on the balance of the sulfates and the calcium aluminate phases. So when looking at early hydration, let's look at the influencing factors. Of course, we have SO3, sulfate. There's a difference in which mineral phase this is present because the reactivity is different. So there's a difference if we talk about gypsum, hemihydrate, anhydrite, or the different alkali sulfates. The alkalis play an important role. The moisture, of course. The storage time, so how long it will be in the silo. And of course, the temperature, because an elevated temperature, for example, might lead to the dehydration of gypsum, and then the available water can lead to further reactions. And in most cases, we need to consider a phase which is called syngenite. So in the cement community, at least, most of the people already have heard the name. So this is one of the most prominent phases we need to consider. And if we look at this graphic, we see here a picture where we have syngenite. These are the needles here. And we also can find some ettringite here. This is also a hydration phase. So syngenite is forming some needles. This is leading to some kind of framework and may have an impact then on how the material is sticking together. The formula of syngenite we see here. So this is a potassium calcium sulfate hydrate. And to get syngenite, there are a couple different reactions possible which can lead to syngenite. So for example, when we have available SO3, form of calcium sulfate, of course some water, and arcanite, which is an alkali sulfate. But there can be much more possibilities. So for example, the reaction of calcium langbeinite with water and arcanite can also lead to the formation of syngenite. So in any case, when we have available SO3, available alkali sulfates, and some moisture and water, this can lead to the reaction of syngenite. And as already said, due to the needle-like structure, there is some bonding in the particles, which may lead to some kind of framework. And of course, it can also lead to accelerated setting because the syngenite is taking out reactive SO3. How to detect this in an X-ray diagram? And what you see here, this is a usual diffraction pattern of an ordinary Portland cement, or in Europe we would call it SEM1. Where do we find this information about, for example, syngenite? And I would like to draw your attention here on this low angle area, on the small peak here. So this is the main peak, syngenite. But there's some more information in the diagram. So once you have syngenite, you will not only recognize this looking here at the main peak at around 9 degrees to theta, there are also a couple of further informations here in the diagram. And to see such low concentrations of these minor phases like syngenite, it is important to have a certain data quality. You need a low noise level, you need a low background at all, and you also need a flat background to be able to quantify even low concentrations of this phase. In this graphic I showed a little earlier, there was syngenite, but also ettringite. And with the next slide, I would like to show you that also ettringite is something which can be easily detected. So here we have another scan of another SEM1 or ordinary Portland cement, and there's something else. So this was the syngenite peak, but you see here on the right side, there's something else. And this is ettringite. And there's even some more information in the diagram, so not only here, but also here. So we can see ettringite, and we can also easily distinguish the ettringite formation from the syngenite formation. How to implement this in our methods? Due to the data quality we have, so the low and the flat background, it is possible to quantify even low concentrations of syngenite. So the limit of detection for syngenite is in the range of 0.2, 0.3 weight %. And this is realized in the Topaz software just by adding this face, of course, and with the remove face macro we do have in Topaz, which is unique for the software. We can also avoid that information is given in case when there are, let's say, low concentrations close to the range of the detection, the limit of detection. So this is realized with the remove face macro. But it's not only syngenite. There are a couple of other phases which can also be tracers for early hydration or can give you a hint that early hydration is occurring. And one thing which is very simple and should not be neglected, this is calcium hydroxide. The mineral name is portlandite. And this was already mentioned in lots of different publications. I just want to cite it here. So, however, free lime can offset or sometimes inhibit this reaction, so this early hydration, by preferentially reacting with water present to form calcium hydroxide. And the reaction formula is pretty easy. So the lime, the free lime plus water is reacting to calcium hydroxide. So very often when you find syngenite or other tracers for early hydration, you will also find an elevated amount of portlandite, of calcium hydroxide. So it's always worth to check a couple of different possibilities. So this was portlandite, which needs to be considered. And there's another phase. Well, the name is a little difficult to pronounce. This phase is called Gergeite. And the intensity contribution to the diagram is illustrated here by the green parts of the scan. So this phase, again, that's called Gergeite. And it's also a potassium calcium sulfate hydrate. And we can easily see this in the diagram. So what I'm showing here, this is a Rietveld plot, where the red curve here, this is the calculated diagram, while the blue curve, this is the actual measured diagram. And in this case, during the calculation, I did not consider Gergeite. That's the reason why you see here a difference between measured and calculated. But I showed here the intensity contribution, which would be related to Gergeite. So we clearly see that this missing intensity here is easily explained by this phase. So also such phase, Gergeite, can be easily detected and distinguished in diagram. And Gergeite is a tracer for elevated temperature. So the formation of this phase takes place at higher temperatures, above 40 degrees, and higher temperatures are increasing the field of stability of this phase. And it is important to keep in mind that this phase, once it is formed, has a very low solubility. So also in this case, the SO3, which we would need for the setting control of the cement, is taken out of the system and not available anymore. There are some further applications. So of course, this is standard of our cement quantification models to consider prehydration tracers like syngenite, but you could also use this to check the stability of reference materials or of your own standards, for example. So in this case, I would like to draw your attention on one cement reference material, which was issued by the VDZ. the certified values you find here in the table on the left side. And if you read the certificate carefully, you will see a small sentence somewhere below the tables. And this is present not only to fill the page, this is really relevant and important information. And this note here is telling us, so slight moisture and CO2 uptake during storage may cause phase transition, like the conversion of free lime or of the sulfate phases, which can be arcanite, aphthidolite, basanite, or calcium langanite, to syngenite. So this is important to keep in mind, because once you open such a vial, you have to be aware that this material will start to react. And after a while, there can be a significant amount of reactions, which then, of course, will also have an impact on the certified values, because some phases will react, so they will not be available anymore. And other phases, for example, like portlandite or syngenite, will be elevated. And I would like to show you in the next slide diagram showing this. So this is a raw data set of an aged VDZ 100 sample. And I would like to draw your attention again on the lower part here of the scan. So looking at the range here from 8 to about 12 degrees. And what we see here is, maybe if you watched the presentation carefully, you will here recognize syngenite, but here's something else, another peak. And this is, so here on the left side, this is syngenite, and this is a calcium aluminate hydrate phase, the so-called AFM group. So in contrast to ettringite, which is an AFT phase, a tree phase, we are talking here about monophase, so calcium aluminate hydrate with an anion group, which could be SO3, which could be carbonate or whatever. And the phases we are talking about, they are called, for example, monosulfate, monocarbonate, hemicarbonate, things like that. So we can even get reactions to such kind of phases. So with the standard methods we have installed on our systems, you can also follow aging processes, for example, of standards, to see if they still can be used or not. So I would like to finish this talk just with a summary. So we can detect phases which are tracers for early or pre-hydration. It is easily possible to distinguish the different phases. Quantification of these hydration processes is a routine task in our installations since a couple of years. And the integration, even in existing method, can be easily done. The only thing which is really important is a certain type of data quality. If we want to detect such minor phases in a proper way, also with low detection limits, we need a low background, we also need a low noise, and we need a flat background. So the air scattering at low angles needs to be controlled properly. So the data quality is an important part here in the whole story. Thank you very much for your attention. If you have any questions or remark, please put them in the chat, please.
Yes, Heine, we have a question. What should be storage time in cement silo not become lumps?
That's really difficult to say because it's not only the storage time. Of course, it also depends on what other conditions are there. It also depends, of course, on the temperature of the let's say of the wall itself. So even when you have some available humidity, of course, then it will precipitate more on the colder parts, on let's say on the walls of the silo. So that's really difficult to say. Of course, the longer the more harmful, but there are not really general rules.
Okay, the second one. How much hydration takes place in one day? Is it possible to quantify it?
Well, we did not yet make studies to really to be able to quantify that, but you will see even small reactions. And what's also very nice is that once you have systems to follow that, you even can easily see difference between what is happening in the mill and then later on in the silo. So it's worth also to consider these two things. So one thing is to control the cement mill, but of course then later on also checking what's going on in the silo. So I cannot give you, let's say, numbers how fast this is taking place, but it's already starting in the mill. For example, in vertical roller mill, there's added lots of water typically to stabilize the milling bed. And then very early you start to see things like that.
The next one. How did the uncertain was calculated in the less common application examples slide?
Can you please repeat it a little louder? I could not understand it completely.
Yeah. How did the uncertain was calculated in the less common application examples slide?
You mean in the table? In the table of the certificate for the VDZ reference material? Do you mean that one?
Yes, I think so.
Well, in the certificate there is
Yes, in the table, yeah.
yeah. So in the certificate there's a description about how the mathematics were done. If you are interested, I can send you a copy of the certificate, then you can see the details. So I don't have the formula in mind, but these are usual statistical approaches. Did this answer the question?
Yes. Yes, I think we don't have any questions anymore.
Okay, then thank you very much for your attention. If you have further questions, feel free to send emails to us. We will be happy to answer those.
Thank you, Heine. Thank you to all. All of you will receive in your email and follow-up email with this recording, okay? So if you have any doubt or if you need more information, you can just write to us. Thank you.